happens to a power plant when the ground itself starts to move. Earthquakes do not just shake buildings, they challenge the safety of entire energy systems. Traditional seismic design focuses on preventing collapse. But for power plants, survival is not enough. These facilities must remain safe, functional, and sealed, even during strong seismic events. Recent engineering research shows that seismic isolation can dramatically reduce earthquake forces by separating the structure from ground motion. Instead of fighting the earthquake, the structure lets it pass. Using advanced three-dimensional simulations, the study found that seismic isolation can reduce structural stresses by up to 70%, regardless of soil type. That means fewer cracks, less damage, and higher safety margins. This is how engineering protects energy, people, and the future. For Science, Salah Lotfy.
Welcome to For Science, Salah Lotfy channel, where global scientific research becomes clear and accessible.
هنا نحول الأبحاث العلمية العالمية إلى معرفة مبسطة مترجمة لك بلغتك.
Ici, la science est expliquée et traduite pour tous.
Ciencia clara, accesible y disponible en varios idiomas.
Wissenschaft, verständlich und mehrsprachig für jeden.
قناة For Science Salah Lotfy Channel. العلم للجميع وبجميع اللغات. تابعنا لاكتشاف المزيد.
Today, I'm diving into a challenge every engineer recognizes, protecting our power plants from the unexpected force of earthquakes. It's a mission that keeps many of us up at night, and one that's only getting more urgent as our infrastructure grows and risks evolve. So, let's talk about a compelling peer-reviewed study that tackles this exact problem: the impact of seismic isolation and soil structure interaction on power plant structures. Behind this research is Dr. Rania Mohsen Elsapai. She's part of the Faculty of Engineering at Cairo University in Giza, Egypt. Dr. Elsapai's work dives deep into structural and seismic engineering, focusing on how to keep critical infrastructure standing tall, even when the ground beneath it isn't. The project was supervised and co-authored by Professor Dr. Hani Ahmed Abdallah. He's a professor of concrete structures, also at Cairo University. With decades of experience, Professor Abdallah has shaped the way we understand and design massive, life-sustaining structures, especially when it comes to concrete and resilience. This research didn't just sit on a desk or vanish into the ether. It was published in Advances in Nonlinear Variational Inequalities, an international journal recognized by engineers and academics worldwide. You'll find it in Volume 28, Issue 7s, published in 2025. And yes, for those who want to dig into the technical details, that's ISSN 10-92-99-NO-X. Now, when I say it's peer-reviewed, I mean it. Here's how the timeline went. The article was received on January 10, 2025. After rigorous feedback and revisions, it was resubmitted on February 27. Finally, it was accepted on March 7. That's the gold standard for scientific credibility: scrutiny, evaluation, and a genuine contribution to the field. So, what's next? In this video, I'll break down the key ideas, the engineering methods they used, and, most importantly, what it all means for real-world power plant safety. Because seismic isolation isn't just a buzzword, it's quickly becoming a cornerstone in how we design for resilience. This is science. This is engineering. And this is For Science. Salah Lotfy.
Earth is made of giant puzzle pieces called tectonic plates, always moving beneath our feet. When these plates suddenly slip, the ground shakes. This is an earthquake. Earthquakes can be tiny rumbles or massive events that topple buildings. Our modern world depends on electricity from power plants, factories that generate power using coal, gas, water, or even atoms. When an earthquake strikes, it doesn't just shake homes, it shakes power plants too. If a power plant fails, millions can lose electricity, right when it's needed most. The real danger isn't just a blackout, but a failure inside the plant that could trigger a disaster. Engineers work hard to protect these plants from earthquake forces. Earthquake energy travels in waves, shaking everything in its path. For a power plant, this is a serious test. Every bolt, pipe, and chip must survive the stress. The safety of entire communities depends on these plants withstanding the planet's powerful movements. That's why designing earthquake-resistant power plants is a top priority. It's not just about keeping the lights on, it's about preventing catastrophe. The challenge: can our power plants stand strong when the ground itself turns violent? Regular buildings are designed to keep people safe during earthquakes, even if damaged. The main goal is safe escape. But power plants must keep working during and after a quake. This is called operational integrity. Hospitals and emergency services depend on power, especially after disaster. That's why power plants are built to much stricter standards. For power plants, almost no damage is acceptable, especially to systems that generate and control electricity. That's why power plant safety is so critical in earthquake zones. The real dangers in a power plant during an earthquake are often hidden inside. Power plants are filled with pipes, pumps, turbines, and control systems. All must work together perfectly. If one key part fails, it can trigger a chain reaction, shutting down the plant or causing disaster. Heavy machinery like turbines can break loose. Pipes can crack, causing leaks or fires. Engineers test equipment on shake tables to see what survives and what fails. Everything must be anchored and flexible enough to move without breaking. In nuclear plants, the stakes are even higher. If control systems fail, operators can lose control of the reactor. That's why every component inside is held to the highest seismic standards. A strong building isn't enough. The heart and brain of the plant must survive too. Making a power plant earthquake-proof means protecting both the building and everything inside. The weakest link, a bolt, a pipe, a chip, can bring down the whole system. Safety is about more than concrete and steel. It's about every detail inside. Backup generators, for example, must be secured to work when needed most. Modern plants use advanced techniques like base isolation to absorb shaking and protect critical systems. Reliable electricity during emergencies demands this level of safety. We can't stop earthquakes, but we can build power plants to withstand them. When the ground shakes, our goal is simple: keep the lights and safety systems on. If you enjoyed this video, don't forget to subscribe to the For Science Salah Lotfy channel for more fascinating science content.
For decades, engineers have designed buildings to survive earthquakes, prioritizing human life above all. Instead of making buildings rigid, traditional seismic design allows controlled movement to absorb earthquake energy. This approach relies on ductility. Think of bending a paperclip. It bends before it breaks. Buildings are designed to sway and deform in specific planned areas, much like fuses in a circuit, sacrificing themselves to protect the whole. This process, called plastic deformation, means parts of the building may be permanently bent or cracked after a quake. The goal isn't to prevent all damage, but to avoid catastrophic collapse and give people time to escape. Engineers carefully plan where the structure should deform to dissipate energy, keeping main columns and floors intact. While this strategy has saved countless lives, it accepts that significant damage is likely. Traditional seismic design works well for homes and offices, but it falls short for facilities that must function after a disaster. The philosophy is life safety, not building preservation. After a major quake, the building may stand, but it's often left damaged and unusable. This limitation is critical for infrastructure that communities rely on. For these, just standing isn't enough. If you want to learn more about the science behind building safety and engineering, don't forget to subscribe to the For Science Salah Lotfy channel. Stay informed and join our community. Ductility is the backbone of traditional seismic design. Steel's ability to bend without breaking makes it ideal for earthquake-resistant structures. During a quake, a ductile building sways, absorbing energy and preventing sudden collapse. Unlike brittle materials that crack and fail, ductile frames deform in controlled ways. Engineers design connections to allow movement, spreading out seismic forces. Plastic hinges, intentional weak points, act like car crumple zones, absorbing energy to protect the rest of the structure. The building may be visibly damaged, but if people walk away unharmed, the design has succeeded. This approach is acceptable for most buildings, where life safety is the main concern. However, for critical facilities, simply avoiding collapse isn't enough. They must remain operational, not just upright. After an earthquake, a building may still stand, but inside, chaos can reign. The swaying that saves the structure can destroy vital systems, pipes, wiring, gas lines, and equipment. Non-structural components aren't built for the same movement as the frame. Broken pipes can flood or leak gas, and power can be lost as conduits snap. Sensitive equipment may be ruined, crippling operations in places like hospitals or data centers. In a bioenergy plant, damaged pipes or control systems can halt power generation. The building stands, but it's useless. Financial losses and downtime can be massive. For critical infrastructure, survival isn't enough. Functionality is essential. The goal is to keep facilities safe and operational, not just intact. A non-functional power plant can disrupt entire communities when they need power most. Standing tall means little if the lights are out. Critical facilities like power plants need more than life safety. They need operational continuity. Modern design moves beyond just protecting the structure, focusing on keeping systems and equipment functional after a quake. Performance-based design sets specific goals, like immediate occupancy or rapid recovery. Techniques such as base isolation, placing buildings on shock-absorbing pads, dramatically reduce damage. This protects both the structure and its contents, allowing quick return to service. Though more expensive, these methods prevent catastrophic losses and long outages. For vital infrastructure, resilient design is a necessity, not a luxury. By prioritizing functionality, we ensure communities recover faster after disasters. The ultimate goal: power plants that keep running, even when the ground shakes. The shaky truth. Have you ever felt the ground shake? It's a strange, unsettling feeling. One moment everything is calm, and the next, the world seems to move beneath your feet. It's a powerful, sometimes frightening reminder of Earth's energy. Earthquakes can strike without warning, leaving people startled and unsure of what to do. Earthquakes happen when the planet's crustal plates suddenly slip, releasing energy in waves, like ripples in a pond. These movements can reshape landscapes and even change the course of rivers. These seismic waves make everything move: the ground, trees, and our buildings. Even the most solid structures can sway and shake, showing just how powerful these forces are. For centuries, engineers tried to fight earthquakes by making buildings stronger and stiffer, but even the toughest structures can fail in a massive quake. Traditional methods often weren't enough to keep people safe. What if, instead of resisting, we let buildings move with the ground? That's the idea behind seismic isolation, a revolutionary approach that's changing how we think about earthquake safety. By adding a flexible layer between a building and its foundation, we let the ground shake while the building stays relatively calm. This technology absorbs and reduces the shaking, protecting what matters most. This protects not just the structure, but everyone and everything inside, especially critical places like hospitals, where lives depend on buildings staying safe and operational. Seismic isolation is about saving lives and building resilient communities. It's science in action, helping us prepare for the unexpected and create a safer future for everyone. If you enjoyed this video and want to learn more about the science that shapes our world, don't forget to subscribe to the For Science Salah Lotfy channel. Stay curious, stay safe. So, how does seismic isolation work? The key is decoupling, a clever engineering solution that changes how buildings respond to earthquakes. Decoupling means separating the building from the ground, so it doesn't follow every jolt or sudden movement during an earthquake. Instead of being rigidly attached, the building is allowed to move independently. Imagine standing on a skateboard. If the board is yanked out from under you, you're likely to fall because you're directly connected to it and feel every movement. But if you're holding onto a sturdy pole, the skateboard might move, but you stay balanced and steady, protected from the sudden motion. Seismic isolators act like that pole. Installed in the foundation, they create a flexible boundary between the building and the ground, allowing controlled movement. These isolators are stiff vertically to support the building's weight, but flexible horizontally, letting the ground move side to side without dragging the building along with it. This flexibility lengthens the building's natural sway, shifting it out of sync with the most damaging earthquake frequencies and reducing the energy transferred. The result? Far less shaking travels up into the building, dramatically reducing the risk of structural damage. Instead of violent, destructive motion, the building sways gently, almost floating on the earthquake's waves, keeping people and property safer. This keeps the structure and its contents much safer, minimizing damage and disruption after an earthquake. By changing how a building connects to the ground, we transform how it experiences an earthquake, turning a dangerous event into something much more manageable and survivable. Decoupling is only half the story. The other half is energy dissipation. Earthquakes unleash huge energy. If a building is rigidly attached, that energy travels up and causes damage. Seismic isolators absorb and dissipate this energy, much like shock absorbers in a car. As isolators flex, their internal components create friction, turning motion into heat. This damping effect keeps the building's movement controlled and gentle. Decoupling lets the building move separately. Dissipation acts like a brake, preventing wild swaying. Isolators are like roller skates with built-in brakes, gliding over the shaking ground, but never out of control. This combination is what makes seismic isolation so effective. It doesn't just block energy, it absorbs and safely gets rid of it. A 1-2 punch against earthquakes, using friction to fight a quake. Now that's smart engineering. Now, let's look at the tools that make seismic isolation possible. Engineers use different types of isolators, each chosen for the building, ground, and local earthquake risks. The main types are elastomeric bearings, rubber-based, and sliding systems, friction-based. Elastomeric bearings include lead rubber bearings, LRBs, and high-damping rubber bearings, HDRBs. The main sliding system is the friction pendulum system, FPS. Each type balances flexibility and energy damping in its own way. These precision-engineered devices are the hidden heroes in earthquake-safe buildings. First up, elastomeric bearings. Think of them as giant, layered rubber and steel hockey pucks. The steel makes them strong vertically, while the rubber allows side-to-side movement. Lead rubber bearings, LRBs, have a lead core that deforms during shaking, absorbing energy, and turning it into heat. The rubber flexes, the lead damps, and after the quake, the rubber recenters the building. LRBs support weight, provide flexibility, and dissipate energy, all in one. That's why they're used worldwide in buildings and bridges. It's a clever blend of materials, science, and engineering. LRBs are like strong, flexible muscles for buildings, ready for the next quake. Next, high-damping rubber bearings, HDRBs, and the friction pendulum system, FPS. HDRBs are similar to LRBs, but use special rubber compounds for energy dissipation, no lead core needed. As HDRBs flex, internal friction in the rubber turns seismic energy into heat, keeping the design simple and reliable. Now, the friction pendulum system is different. It uses a curved steel dish and a sliding component. During a quake, the slider glides along the dish, gently lifting the building and letting gravity recenters it. Friction between the slider and dish dissipates energy. FPS is especially effective for large, heavy structures. Each system uses physics to keep buildings safe. Whether it's rubber or sliding steel, the goal is the same. Let the building move, but keep it safe. That's seismic isolation in action. Before isolators are used in real buildings, they're tested on massive shake tables. These platforms simulate real earthquake motions, letting engineers see how structures perform. HDRBs are often tested for their consistent, predictable damping. Scientists compare isolated and fixed base models side by side. The difference is dramatic. This testing is crucial for essential facilities like hospitals and power plants, where failure isn't an option. Seismic isolation protects not just buildings, but the vital equipment inside. Rigorous lab science leads directly to real-world safety. Let's visualize the impact of seismic isolation, a technology that's quietly revolutionizing how we build in earthquake zones. Imagine two identical office buildings standing side by side. One is built on a traditional fixed foundation, while the other rests on advanced seismic isolators designed to absorb ground motion. Suddenly, an earthquake strikes. The fixed base building is yanked violently by the shifting earth, bending and swaying. Inside, chaos erupts. Desks topple, computers crash to the floor, and the building's frame groans under the stress. But in the isolated building, as the ground shakes, the isolators flex and absorb the energy. The building glides smoothly, barely moving compared to its neighbor. Inside, it's a different story. Desks remain steady, computers stay put, and people experience only a gentle, almost soothing sway instead of panic. The structure and all the non-structural elements, like ceilings, lights, and partitions, are protected from damage, preserving both safety and function. These isolators act like shock absorbers, creating a calm oasis in the midst of a seismic storm. This side-by-side comparison makes it clear. Seismic isolation doesn't stop earthquakes, but it completely transforms how buildings experience them, reducing damage and disruption. The difference is night and day. One building is battered, the other stands strong and unscathed. It's not just about survival, it's about ensuring safety, comfort, and resilience for everyone inside, even after the shaking stops. For cities in earthquake-prone regions, seismic isolation is a true game changer, offering peace of mind and long-term protection. It's a remarkable feat of engineering, one that saves lives, protects investments, and keeps communities thriving. The science is visible in every quake, as isolated buildings consistently outperform their conventional counterparts. That's the power of decoupling, a simple idea with extraordinary results, keeping people and places safe when it matters most. So, what does this mean for us? Seismic isolation is a powerful tool for a safer world. We can't stop earthquakes, but we can design buildings to stay functional after them. This shift is saving lives and protecting communities everywhere. For people, it means safety and peace of mind. For society, it means less damage and faster recovery. Isolated bridges stay open, hospitals keep treating patients, and data centers keep running. As technology advances, engineers are developing even smarter isolation systems, using new materials and real-time sensors. Every new isolated building is a step toward a more resilient future. Seismic isolation is a beautiful example of human ingenuity, using physics to solve nature's toughest challenges. Next time you hear about an earthquake, remember the hidden heroes in our foundations. It's not magic, it's science, making our world safer every day.
Nuclear power unlocks immense energy from atoms, powering cities without greenhouse gases. But splitting atoms creates radioactive materials that must be contained at all costs. The European Pressurized Water Reactor, or EPR, is designed with defense in depth, multiple independent safety layers. Its most visible feature, the containment buildings, colossal fortresses built to keep everything inside, no matter what. Unlike ancient castles that protected people from outside threats, these fortresses protect the world from what's inside. The iconic dome isn't just a roof. It's the outer shell of one of the strongest structures ever built. This is the foundation of nuclear safety, robust engineering to ensure nothing harmful escapes. Over the next few scenes, we'll peel back the layers of this fortress. We'll see how the EPR's design makes it one of the safest places on Earth. Let's step inside and discover the engineering marvels that keep us safe. Welcome to the heart of nuclear security. Make sure to subscribe to For Science Salah Lotfy channel for more fascinating science content. At the core of the EPR's safety is the primary containment, a massive sealed vessel encasing the reactor and its systems. Its job: contain all radioactive materials, even under extreme pressure and temperature. Built from thick, pre-stressed concrete and lined with steel, it's engineered to be completely leak-tight. Imagine a soda can designed to withstand unimaginable pressure. This is that on a colossal scale. Even in a worst-case scenario, the primary containment holds firm, preventing any release. Pipes and cables pass through special airtight seals, maintaining the perfect barrier. This structure is constantly monitored, always ready to perform its vital function. The primary containment is the ultimate guardian of the reactor core. It's the first and most powerful line of defense. Without it, nuclear safety wouldn't be possible. Surrounding the primary containment is the secondary containment, the massive dome you see from outside. This structure shields the reactor from external threats, hurricanes, earthquakes, even aircraft impacts. It's not just a wall, but a second fortress, absorbing energy from disasters and protecting the systems within. If the primary containment were ever compromised, the secondary containment steps in. The space between the two is kept at lower pressure, so any leak is drawn inward, not out. Escaped particles are trapped and filtered before any air is released. This double-wall design is central to the EPR's safety. It's an active system, not just a passive barrier. Together, these layers create a near-impenetrable shield. Why two containments? Redundancy. In nuclear engineering, you never rely on a single system. The outer wall absorbs external impacts. The inner wall secures the reactor. This separation means even if one fails, the other stands strong. The buffer zone between them gives operators time to respond, turning emergencies into manageable events. This dual barrier approach is about confidence, planning for the physically possible, not just the probable. Two massive, independent barriers show the EPR's uncompromising commitment to safety. It's the ultimate safety net for people and the environment. The engineering behind these structures is staggering. The outer wall, nearly 2 meters of steel-reinforced, high-density concrete, thicker than a car is wide. Inside, the primary containment adds over 1 meter of pre-stressed concrete, bound by steel cables tightened to immense tension. This pre-stressing makes the concrete incredibly strong and crack-resistant, even under extreme pressure. Think of squeezing a stack of books tightly. Pre-stressing holds everything together. These walls aren't just buildings. They're static, passive safety systems with no moving parts to fail. Their strength comes from sheer mass and brilliant engineering. They form a fortress, a silent shield protecting us from the power within. This is engineering in service of humanity, ensuring clean energy stays safely contained. The EPR's containment is a testament to our ability to manage the atom's power.
Earthquakes aren't just about shaking buildings. They're about the invisible forces at work beneath our feet, forces that can turn a calm city into chaos in seconds. It's about the ground they stand on, the very foundation that supports our homes, offices, and lives. The soil beneath plays a crucial role in how structures experience seismic waves, acting as either a buffer or a magnifier for the energy released. Imagine standing on solid pavement versus a wobbly waterbed during a quake. One feels stable, the other unpredictable and dangerous. Different soils can either dampen or amplify shaking, making some areas much riskier than others, even within the same city. That's why engineers study soil so carefully, to build safer cities and protect lives. knowing the ground is an active participant in the earthquake drama. A building's safety can vary greatly depending on the geology beneath it. What lies below can mean the difference between survival and disaster. Before construction begins, understanding the ground is essential. Testing, drilling, and analyzing to ensure the safest possible foundation. The interaction between soil and structure is key to earthquake resilience, shaping how buildings respond when the earth moves. By appreciating soil's role, we can better prepare for seismic events and build a safer future for everyone. If you found this video helpful, don't forget to subscribe to the For Science Salah Lotfy channel for more fascinating science content. Meet the main players in our soil story: solid rock, dense sand, and soft clay. These three types of ground beneath our feet shape how the earth moves during an earthquake, and how buildings respond to that movement. Each soil has its own personality. Dense sand and gravel are gritty and strong, while soft clay is sticky and flexible. The differences between them are more than just texture. They affect the safety of our cities. Bedrock is incredibly stable, barely budging when seismic waves hit. It delivers a sharp, quick jolt during quakes, but doesn't let the shaking linger. Buildings anchored to rock foundations experience less amplified shaking, making them safer during earthquakes. Dense sand and gravel slow down seismic waves, which increases the intensity and duration of shaking compared to rock. Structures built on sand tend to sway and move more than those on solid rock, making them more vulnerable to damage. Soft clay is the most unpredictable. It traps seismic energy, causing intense, prolonged shaking that can last much longer than on other soils. Buildings on clay face the most violent and damaging motions, often suffering the worst effects during a quake. Each soil type presents unique challenges for engineers and architects when designing safe structures. By understanding these differences, engineers can design buildings that are more resilient and better able to withstand earthquakes. In the end, it's all about applying the right physics to keep us safe. Soil structure interaction is a dynamic dance during quakes. The ground shakes the building, and the building affects the soil. This feedback loop creates a unique seismic environment. Heavy buildings influence ground motion, like a battleship in a tub. Resonance can amplify shaking, especially on soft clay. Engineers use this knowledge to design safer buildings. Tailoring structures to their geological conditions is crucial. Understanding this interaction moves us beyond one-size-fits-all solutions. Science is in the details. Seismic isolation is a revolutionary engineering approach that truly changes the game, making the type of soil beneath a building far less critical than ever before. Instead of relying solely on the ground's natural stability, engineers now have a powerful tool to protect structures from earthquakes. Buildings are carefully placed on flexible bearings, which act as a buffer, physically separating them from the violent shaking of the ground during an earthquake. When an earthquake strikes, only the isolators move and absorb the energy, while the structure above remains remarkably stable and protected from harm. It's a bit like a magician's tablecloth trick, where the table stays still as the cloth is whisked away, except here, seismic energy is absorbed and redirected, sparing the building. This technology dramatically reduces the impact of soil amplification, which can otherwise make earthquakes much more destructive for certain locations. Isolated buildings also avoid dangerous resonance effects, which can cause catastrophic swaying and damage in traditional structures. Seismic isolation offers universal protection, making it effective across all soil types and in a wide variety of environments, from dense cities to remote areas. This innovation allows for the safer construction of critical facilities like hospitals, schools, and homes, ensuring they remain operational after major quakes. By uncoupling buildings from the ground, we outsmart the very physics of earthquakes, turning a once unpredictable threat into a manageable challenge. Seismic isolation is science in action, protecting lives, preserving infrastructure, and shaping a safer future for everyone.
Ever notice how buildings seem unshakable? But just like us, they feel stress from wind, temperature swings, even tiny ground shifts. Over time, these forces add up, causing cracks and other problems. Think of a building like a Jenga tower. A little nudge here and there, and things can start to shift. We want our homes and workplaces to be safe havens, so engineers are always searching for ways to make buildings stronger and more resilient. It's not just about stacking bricks anymore.
It's about using science to outsmart stress. By understanding how forces affect materials, we can invent new technologies that help buildings relax and last longer. As cities grow and buildings get taller, this innovation becomes even more important. Our mission? Build structures that can handle whatever comes their way without breaking a sweat. Thanks to science, we're making real progress. The future of building is about safety, durability, and peace of mind. Imagine a world where our buildings are as calm and reliable as we want them to be. That's the goal, and we're getting closer every day. Science is leading us to safer, smarter buildings. Let's look at older buildings. Ever seen a crack in a wall or a door that won't close? That's stress in action. These structures were built to be rigid, but that rigidity made them vulnerable. Like a dry twig, they'd snap instead of bend when forces hit. Over years, small movements and temperature changes caused cracks, leaning walls, and sagging floors. Even tiny shifts could lead to big problems, windows cracking, tiles popping. The old way of building meant constant repairs and a losing battle against nature. Engineers realized buildings needed to work with, not against, the environment. The dream, structures that could flex and absorb stress, not just resist it. This shift in thinking set the stage for a new era in building design. Instead of fighting nature, we started learning from it. The result? Buildings that last longer and stay safer. It's a smarter, more sustainable approach, and it's changing everything. Fast forward to today, engineers have created technology that lets buildings breathe and manage stress. Studies show these new structures have up to 70% less internal stress. That's like lifting a huge weight off a building's shoulders. Not only is stress reduced, but movement, like shifting walls or sagging floors, is minimized too. Fewer cracks, fewer repairs, and a much longer lifespan. Doors close smoothly, windows stay intact, and floors remain level. The whole building works as a stable, unified system. There's even a bonus. These designs help protect against radiation in specialized environments. Fewer cracks mean better containment and safety. One breakthrough, multiple benefits. It's a leap forward in how we protect people and property. Science isn't just making buildings stronger, it's making them smarter, and that's a win for everyone. Compare the old and new before. Buildings were tense and brittle, always at risk of cracking. Now, with new tech, they're flexible and resilient, like athletes instead of statues. Stress is slashed by up to 70%, and displacements are kept in check. That means fewer repairs, less worry, and buildings that last for generations. These aren't just hopes, they're proven results. Engineers now design with confidence, using real data to build safer structures. We're replacing guesswork with certainty, and vulnerability with resilience. This is more than preventing cracks. It's redefining building safety. Our structures are ready for anything, from daily weather to extreme events. Science and engineering are solving real-world problems, making life safer for everyone. The future of building is here, and it's strong, smart, and secure. That's the power of innovation. Now that's something to build on.
All right, let's break down what these new technologies really mean for us in the world of power generation. I'm talking about things like advanced monitoring systems, predictive maintenance powered by AI, and new materials that are more durable and efficient. First, lifespan. Modern tech is extending how long power plants can operate safely and effectively. With real-time sensors and smarter analytics, I can spot issues before they spiral out of control. That means less wear and tear, and in the long run, power plants stay online for years longer than before. And here's a big one: maintenance. Instead of sticking to a rigid schedule, I'm shifting to a fix-it when it needs fixing mindset. Predictive algorithms flag potential problems, so crews only step in when it's actually necessary. That slashes routine downtime and keeps everything running smoothly. Now, this boost in reliability also gives me more flexibility in choosing where to build new plants. Before, I was limited by geography and easy access to infrastructure. But with compact, resilient technologies, I can consider sites that weren't practical in the past. Think remote regions or places with harsh conditions. That opens up a whole new world for energy distribution. But the impact doesn't stop at the plant gates. Let's zoom out. More resilient and efficient power plants mean fewer disruptions to the energy grid, which keeps the lights on for everyone. That's huge for both public safety and economic stability. Environmentally, longer plant lifespans and fewer breakdowns mean less wasted material and better resource management. Plus, integrating cleaner technologies directly reduces emissions. Every step helps. From an engineering economics perspective, cutting unplanned outages and extending asset life saves serious money, both for plant operators and for end users. Those savings can flow back into the system, funding even more innovation. So, bottom line, these new technologies aren't just about making things a little better. They're reshaping the entire power generation landscape, making it stronger, smarter, and more sustainable. And for those of us in the business, that's not just exciting, it's essential. Thanks for tuning in. If you want to learn more about how these innovations are shaping the future of energy, stick around. I've got plenty more to share. And don't forget to subscribe to the For Science Salah Lotfy channel for more fascinating updates and insights.
What keeps skyscrapers from tumbling down when the ground shakes? Seismic isolation, folks. Seismic isolation is a game changer in engineering. Imagine a world where buildings sway gently instead of collapsing during earthquakes. That's the power of seismic isolation at work. By decoupling a structure from ground motion, it absorbs and deflects seismic energy. This revolutionary technique is backed by cutting-edge research, like ABAC's 2023 finite element modeling and time history analysis of the El Centro earthquake. Seismic isolation isn't just a fancy concept. It's a crucial investment in our safety, our buildings, and our future. This isn't just about protecting structures. It's about safeguarding lives, ensuring energy infrastructures remain operational, and preserving our way of life. So next time you see a skyscraper standing tall, remember, it's not just concrete and steel. It's science and engineering working tirelessly to protect us all. This is how engineering protects energy, people, and the future. This is For Science, Salah Lotfy.
Exposing the dedication powering breakthrough science, today we shine a spotlight on the remarkable individuals advancing engineering excellence. Their commitment shapes the future. Let's celebrate their impact. Before we conclude, I wish to express my deepest appreciation to the researchers behind this outstanding work. Dr. Rania Morsinis-Sabari from Cairo University's Faculty of Engineering has shown unwavering dedication and delivered invaluable contributions to this research. My sincere gratitude also goes to Professor Dr. Hani Ahmed Abdallah, Professor of Concrete Structures at Cairo University, whose scientific leadership and expertise in structural and seismic engineering have been pivotal. Their collaborative efforts exemplify academic rigor and offer vital insights into safeguarding critical power plant structures against seismic threats. And to you, our viewers, thank you for supporting scientific inquiry. Please share your thoughts and questions below. Your engagement fosters informed discussion and drives progress in engineering. This is Professor Dr. Salah Lotfy, signing off, for Science Salah Lotfy channel.